Hi. In this video and also the next video, we will build some arithmetical logical unit, but actually a very simple ALU. It will only support a few operations. And I cannot show you the most realistic and most elegant hardware design for that. I'm a mathematician and the electrical engineers can do that way better than I possibly could imagine that I possibly could do. But it's about seeing by ourselves how in general, in principle, such a device could be created. And most of all, how could we describe this formally, what this device is actually doing, so that we can come up with certain notations that we later can use for describing the instruction set architecture of a computer. The first main component of our ALU is a register bank with 16 registers, and each of these registers can store 16 bits. And before I describe this ALU register bank more formally, I will show you my register bank in Circuitverse and how you can use it and how, of course, you can build it by yourself. This is the demo circuit for my register bank. And you see here a few inputs and lots of outputs. Let me first explain you some of the outputs. The register bank has 16 registers. Each of them can store 16 bits. And these registers are labeled from 0 to 15. And actually I'm using hex digits for that. So you see they are labeled from 0 to hex F. And this percentage sign followed by some label, you can read as register with some given label. So for example, this here would be register 4. And if I connect it with some output device, I can see the bit pattern. So register 4 just stores currently the bit pattern with only zeros. And so does register 2. Now, if I want to store some bit pattern in a register, I can use this input device for the bit pattern that I want to store. And with this input device, I can select the destination, the ID of the register that should be overwritten with this bit pattern here. So let's say I want to store it in register 2. Select here the ID, hit the clock, and boom, here it is. If I want to store this bit pattern in register 4, I can hit here the clock again, and boom, here it is. Now you see I was obviously too lazy to connect all these registers with output devices, and actually I will just use this outputs here for debugging. You will see there is quite a lot of wiring going on, so things can go wrong, and then it's good to actually see what is the content of a particular register. But usually I will not only use the registers for storing data, but also for using them as an operand for an operation. For example, I want to add register 2 with register 4 and then store the result in register 6, for example. And so I just need 2 of these registers as an operand. And for getting an operand, I use, for example, here this source 0 or source 1. So 0 is always the first operand and source 1 the second operand. And then if I want to add register 2 with register 4, then I would use here the ID 2 for the first operand and here the ID 4 for the second operand. And then if I would store the results in register 6, then the destination for the bit pattern computed as the sum actually of these 2 registers would be the new bit pattern here. And the destination can be selected here. Now, before I continue to show you how this is actually then part of the ALU, I will first show you how to build this register bank. And for that, I will kill my current implementation of this circuit up here and then rebuild it step by step. For a single register, I use a D-latch flip-flop with 16 bits. And in the beginning, I will just use 2 registers in total. And later, it can be increased with some patience and effort to 16 bits. So in order to fill it with some bit pattern I need a 16-bit input device, and this already gets the name %test. I also need a clock signal, and I also need some selector for the destination. I already showed you how to use this demultiplexer so that we can connect the destination bit pattern and the clock signal with the destination register. And I also showed you that it's convenient to use this splitter here, where I combine first the destination bit pattern with the clock signal, and this allows us to have a simpler way of wiring things. Now this combined bit pattern will go through this demultiplexer, so I have to increase the bit width to 17 actually. Then with the destination bit I can select where this should go to, and here I change the orientation to right, and this I actually need twice. Now this should already work for 2 registers. Basically that was already shown in a previous video. Now still, let's check if the clock is off. I can change the destination without immediately overwriting the content. Then I turn on the clock and turn off the clock, change the bit pattern, change the destination. It works. Now what I will do, and I just show you this in the fast motion, I will create altogether 16 registers. I will change the demultiplexer so that we have 16 outputs. Actually I can change this right away. That means I have to change the control signal size to 4. And then you see this requires some patience to do the wiring correct. And also this destination input device will get a bit width of 4. So this part I already can connect, and the rest I have to do in some quiet time. So this is finally done. Next I can choose some register for some operation, for selecting what register I want to use. I need 4 bits to identify it. So this is source 0, and then I also use a multiplexer with a bit size of 16, and the control signal has 4 bits. And now this 4 bits give us the control signal, and then I just have to again do the wiring. For example, this first register here will be connected with the first input field here, and so on. And that's just one of it, one selection for a register. We actually need this twice. So this selects source 1. And that's actually it, except for some output devices that we still have to connect. An output device for the selected source 0, which has 16 bits, and also for source 1. And then also for debugging purposes, output devices for register 0 to register 15. So this is now our register bank. Now let's see how the layout for this building block looks like. Well, I want to have the clock down here, but the rest is okay. First the bit pattern for the destination register, the ID of the destination register, IDs for the source registers. Also here the output devices look good, so let's save it. And then I have to reconnect a few things here. Also somehow this changed here. So now also build some demo circuit for it, and I also will check my new rebuilt register bank in this demo circuit. In software development, you usually do not solve a problem in just one step, or you can't solve a problem in just one step. You usually begin with a small subproblem, think about how to solve that, and then you try to improve this initial attempt so that you can solve a larger subproblem. And then you have this cyclic kind of development where you always go forth and back, and hopefully you go more forth than back, so that you each time get closer to the actual solution and that you only have a finite amount of cycles. Something similar we would face with our ALU project. This register bank so far is some initial attempt to solve a certain problem, or a certain problem that we already can identify, that we, for example, need an operation like adding a register with another register and then storing the result in a third register. Other problems we haven't considered so far, and usually we would now continue and then see that certain things are missing, and then we would go back. Now here I want to make a shortcut. I will already show you that certain auxiliary features will be required and how to implement them. One problem that we will face is the need to extend a bit pattern to a larger bit pattern with more bits, and the constraint, for example, would be that the unsigned value represented by these bit patterns should be the same. And of course we know how to do that. We have to zero extend these bit patterns. That means the most significant bits in this extended bit pattern are just set to 0. In the more formal description I will use this notation where I also want to point out that a certain bit pattern, for example here y, gets overwritten with a bit pattern of x in such a way that the unsigned value of x and the unsigned value of y is the same. For implementing this zero extension, or I call it zero fill, create a new subcircuit, use a 8-bit input device with this given 8-bit bit pattern that I called x. Then also use a 8-bit const input device. This will give us the extension, the zeros. And then we need a 16-bit output device where we have this final zero extension. And then I combine the bit pattern that we have with a splitter like that. So I just changed the orientation or the direction, and now I combine the bit pattern that is given as the least significant bits with the zero extension as the most significant bits, and this becomes the generated output, the generated zero extended 16 bits. Now, because we want to use this later, make sure that this layout is nice so that we have a slim and slick building block. you already might guess what comes next. When we use a bit pattern to represent a signed value, then we also want to extend it in such a way that it's preserving this value, this signed value. And we know how to do that. If this signed value is non-negative, then we also just extend it with zeros. And otherwise, if the value is negative, we extend it with ones. And in the more formal description, I again use this notation by Knuth, where I make clear that the bit pattern of y gets overwritten in such a way that its signed value afterwards equals the signed value of x. Again, I call this subcircuit sign fill instead of sign extension because it's shorter. Now, in order to implement the sign extension, I first of all need this 8-bit input, and for the extensions I need two const inputs with 8 bits, one with the zeros and one with the ones. 1, 2, 3, 4, 1, 2, 3, 4. Okay. And then I also need this 16-bit output. Let's say here. Now, in order to do the correct extension, I somehow have to use this most significant bit to select what kind of extension I want. So first I use a splitter to pick up the most significant bit. So I split 8 into 7 and 1. And then this most significant bit will be used as control bit for the multiplexer, which then provides me the right extension. So the bit width of the multiplexer is 8. And now I have to combine this here with the correct extension. And for that I again use a splitter like in the 0 extension. So I split 16 into 8 and 8. So now here I want to use the direction up because then it's easier to avoid too many weird crossings in the lines. The least significant bits I get from here, from the input from this bit pattern that I called x. So I connect this with the least significant bits, and the most significant bits are what I get from this multiplexer. And now you check if the most significant bit here is set to 1, I get a 1 extension, and otherwise always a 0 extension. It also will be useful for us to have a left shift operation. And in this case, it's not about extending a bit pattern, it's about changing a bit pattern. We have a 16-bit pattern, x, and first we want to do a left shift. That means we have 8 new bits at the least significant positions. Those will be set to 0. That means now we have a 24-bit pattern, and this will be truncated to the 16 least significant bits. So how to do that by example is kind of simple to see. But here you see this description is not very brief. And here the formal description is really helpful, that we basically first take the unsigned value of this bit pattern, multiply it with 2 exponent 8. This means then we do a left shift by 8. And we also make clear that the new bits are set to 0. And the fact that we then truncate it to 16 least significant bits is just represented by a mod operation with 2 exponent 16. In Circuitverse, create a new subcircuit. I called it left shift by 8, and then we need first a 16-bit input. Again, it's not about extending the input, it's about changing it. And a 8-bit const input that will give us the new bits all set to 0. And then I also need a 16-bit output. First I will use from this bit pattern only the 8 least significant bits. So I use a splitter that splits 16 bits into 8 and 8. And now here I get the least significant bits from the input bit field, and these are the bits that I actually need. I don't need this 8 most significant bits, they will just vanish. Then I use this splitter again with a different direction, left, for combining the least significant bits from the input with this extension. For now, for this least significant bit, this is actually an extension, and that's it. Now you see, if you change something here in the most significant bits, you don't see any difference in the output. But if you change here this bit, then this bit pattern here, or this part of the bit pattern, is the part here, and here you have this 0 extension from up here. Now, because we also want to use this later, make sure that you have a nice layout here. The next modification is even easier to realize, but maybe at this point it's not so clear why it possibly could be useful. But think of this examples that I gave for conditional jumps, where we always do this subtraction, but afterwards we just check the status flags of the adder. And in these cases, you just do a subtraction. You don't care about the result, you just care about the status flags. So it might be a good thing to have a register where you always can write to, and you don't have to care if this register is already used for storing some useful data. So you want to have a register that you can use like a trash can. And it's also sometimes nice to have a register where you always read a 0-bit pattern if you read from it. And another motivation, building a so-called 0 register is something very cheap, because you don't need flip-flops for it. So in Circuitverse, you just go to the registers bank, and then we kill this register, the 0 register, and we use a const input with only zeros and 16 bits as a content of this register, of this imaginary register. So if we read from this register 0, we get this 0-bit pattern, and if we write to it, it just vanishes. Now in the end of this video, I want to do some kind of a brainstorming to give you an idea how we could move on from this point to the next step. For this brainstorming, I created a new subcircuit basically with a copy of my registers demo so that we can see things. Let me change this input device into 8 bits. So I now can't directly connect it, but I want to use this 8 bits for describing a bit pattern that should be stored, for example, in register 1. So I choose here as destination register 1. So now I first have to extend it, for example, with zeros. So I use this tool here to get the 0 extended 16-bit pattern connected with this input. And now if I hit the clock, this bit pattern, the 0 extended bit pattern, gets copied into register 1. If I want to see the content of register 1, I, for example, can choose here register 1. So this is the content of register 1. Now let's say in register 2, I want to store the sign extension. So I select here that this will display the content of register 2, or already does show this content. It's currently containing the 0-bit pattern. Then I use here the sign extension, hit the clock, and here we go. Now next I want to, for example, add this bit pattern with this here. So that means the bit pattern of register 1 with register 2, and I want to store the result in register 3. So I already can change that here. And then I will replace this here with a adder, with our adder that also has this accumulator. And then the bit pattern that should be stored comes here from this S. The operands are this register source 0 and register source 1. Actually, we can discuss about which should be operand A and which should be operand B. But here it actually doesn't matter. Now I want to use an addition, so I use here 0, and I also need a clock signal. Now it's important to understand that if I now hit the clock here, the content of these registers are added and the results stored in the accumulator. So that happened now. But it's still not in register 3. But these registers, the content of these registers are already used by the adder. So I now could modify the content of these registers, and I also can here now show what is the current content of register 3 before I copy the accumulator into the register. So if I now hit the clock, this copy is carried out. So now we have the expected result. Now you also can now play around with these tools and get an idea how we could proceed from here on.